Lab Talk with Laura. Listen, I implore ya. Won't never bore ya. Lab Talk with Laura. Always more in store, ya. Lab Talk with Laura.
Welcome to Lab Talk with Laura. I'm here today joined by a few guests from UMass Amherst. First, we have Nigel Golden, who is a doctoral student in the Environmental Conservation Department at UMass Amherst. He is a Northeast Climate Science Center Graduate Fellow, an NSF Graduate Research Fellowship Fellow, and a Natural Geographic Explorer, or is it just Nat Geo?
You could say Nat Geo Explorer.
Nat Geo Explorer.
Yeah.
He's originally from Milwaukee, Wisconsin. He did his undergrad at UW Stevens Point and studied biology and wildlife ecology. And currently he is studying the changing Arctic and its impact on conservation in wild places. Thank you for joining us, Nigel.
I'm glad to be here.
Cool. Next up, we have Ruthie Halberstadt. Did I say that right, Ruthie? Halberstadt. She is a doctoral candidate in the geoscience department at UMass Amherst. She got her bachelor's and master's in earth science at Rice University in Houston, Texas, and she's originally from Durham, North Carolina. She studies ice sheets, climate, and sea level. Thank you for joining us, Ruthie.
Thanks for having me.
And last, my guest co-host for today is Taylor Ortiz, who is a local comic studying comedy at Hampshire College. He's originally from Houston, Texas, and you can catch his sketch comedy TV show Fever Dream on their YouTube page, Felt Waffle. Thanks for joining us, Taylor.
Glad to be here.
Okay, so first up, Nigel, could you maybe just tell us about the research that you do?
Sure. As you referred to earlier, I am studying the changes in the Arctic and their impact on conservation and wild spaces. The species that I study is Arctic ground squirrels, and where I study them at is Denali National Park in Alaska. These two things are important, so the importance of the work gets pretty significant. Denali is a UNESCO World Heritage Site. It's a biosphere reserve in the interior of Alaska, and so amongst a cohort of nations, just not the United States itself, they've determined that it has universal value. And as a national park, it is held as a cornerstone in conservation because it holds large, uninterrupted tracts of land, which are important for many animal species in general. It's actually about the size of Maine if people want to know what the park was like. So it's a pretty big park. And Arctic ground squirrels are important. They're considered a keystone species because they are generally on everybody's dinner tray in Denali National Park. So grizzly bears, wolves, golden eagles, foxes, they're kind of, everything in there almost kind of relies on them as a food item. And so you kind of think of it as, for humans, imagine if our most stable crops were suddenly not available. So I'm looking at how climate change is impacting not only the place that they live in, but I'm also looking at how climate change is going to affect their persistence in that park.
When you say value, do you mean to science or the world? Like what value does it have just chilling there?
So the Denali it's a national park, so it's maintained by the National Park Service, which is a federal agency. And so they're federally mandated with preserving unimpaired natural and cultural resources for our current generation, that would be us, and for future generations, for those of us who decide to have kids. And so because they are federally mandated to preserve this place, there's a lot of value to be held there, particularly, which is why it's also labeled a biosphere reserve. So out of all of the wild places that are left intact on Earth, this is one of the largest places on the planet that has the lowest amount of impact from human presence.
So you brought up the predators that all feed on the ground squirrels.
Yes.
So first of all, have you gotten attached to any ground squirrels?
I think I'm attached to all of them in general.
Okay.
Yeah.
That's a community that you really are connecting with.
I really do connect with the ground squirrels.
Did you
They're
study
so
them?
cute.
When did you start studying them?
So as a undergrad, I did 2 research expeditions to Northeast Siberia. And while I was there, I studied Arctic ground squirrels there as well. And it kind of continued over into my dissertation work here at UMass.
Cool. Do Arctic ground squirrels look different than the squirrels we see around campus, for example?
Yeah, so the squirrels you see around campus, those are tree squirrels, really long tails, very slim profile. And they don't actually hibernate during the winter. They enter more of, just an inactive state, but they still are awake. They're able to move around. And you still actually see them leaving, their trees and coming down to try to find the food that they cached. Arctic ground squirrels are more akin to black-tailed prairie dogs, which we have in, really central parts of the United States. So they live in the ground. Their homes are in the ground. They dig these huge colonies. And compared to the tree squirrels that we have here in the Northeast, they are hibernating 7 to 8 months out of the year. And so for, most of the year, they're inactive underneath the ground. Bodies are below zero, below freezing. And so actually, out of all of the recorded body temperatures for animals that hibernate, they actually have been recorded to have the lowest body temperature.
Wow. So they just chill at zero. What did you say, 0?
Below freezing point.
Below freezing.
Yeah.
They just chill below freezing for 7 to 8 months of the year.
Exactly.
Wow.
Are they scared of like people? Because you were talking about how like there's a very minimal impact. Do they like know to run away, or do they think like, oh shoot, this guy might have some like Cheez-Its? Like, what's their like reaction to seeing humans?
Yeah. So a standard procedure in a national park and in many places that you're not supposed to feed wildlife. And so at the visitor centers, there are Arctic ground squirrels there. Human structures are really good for ground squirrels because it provides them a good starting point for them to burrow into the ground. And it's typically not surrounded by grizzlies, bears, and golden eagles. So there is some interaction between humans and ground squirrels. And the ground squirrels that are closest to the human spaces are more likely to interact with people. But when I'm in the wild, which where I am doing my field work at, the Arctic ground squirrels, they exhibit this type of behavior where one is, like being this vigilant guy or girl or gal. And what they do is when they detect a predator, and I would be considered a predator, they emit an alarm call. And so all of the other ground squirrels that are in that colony, they'll stop whatever they're doing, like they'll prop up and like they're looking around, they're seeing what is the reason for this alarm call, and then they'll start emitting the alarm call as well. And so that's kind of the engagement that I have with the ground squirrels that aren't around people.
Can you make like, what does the alarm call sound like? Are you able to do it, or for those of us who haven't had the pleasure of hearing it firsthand?
Let me get back to you.
Okay. That's okay. You don't have to do that.
Came in here as a man of science. You have to do calls.
It's like a squeak with a twill. It's squeak. That doesn't do it any justice, but just imagine that, like these high mountainous areas, and so it's bouncing all over the place.
So do they all start doing it at once too? Like you can hear or is it just like one and then they all like go back underground? So
one will make the initial call, and then others in the colony or in surrounding communities, they'll also emit the alarm call as well.
Okay.
Yeah, it's a type of vigilance behavior where everybody kind of has some type of positive benefit from it. The downside is that for the one that makes the alarm call, they're kind of giving away their position. But at the same time, they're letting that individual know, whether it be me or another animal, like, hey, I see you. I know you're there. Right. And you can try to catch me, but you're not going to catch me.
So what kind of things are you looking at when you go out in the field?
Right. So one way we look at how a species, the health of a species, is by studying their populations. And one way of doing that is by trying to count how many is in that population, how are they distributed, and what factors in their environment or within their population is like kind of impacting the health of that population. And so one way of doing that is to count all of the individuals within that population, which is just kind of impossible. and that would be called a census. One, Denali National Park is just way too huge.
Okay.
I can't backpack the state of Maine in wilderness during the summer. And it's also just kind of, impractical to expect to count all of the individuals within that population. The same goes for plants. So one way we get around this is by coming up with the estimate of the density of that population, the density or the abundance. And so I use a distance-based sampling technique. Essentially, I am walking straight lines in the national park in specific habitats, in a replicated number of habitats, and I'm counting the amount of individuals that I see. And essentially what it boils down to, using that information, I can extrapolate or project out to the entire Denali National Park and come up with an estimate for how many Arctic ground squirrels there are, how they're distributed, and what are some of the drivers that is affecting that distribution and health of that population.
Is there a basis, like do other people have previous records of this for you to compare the measurements you're taking, and are you seeing any kind of trends?
So one of the really cool aspects of this project is that, well, unfortunately, there's not a long-term data set for their population in this part of Alaska, at least. And also more so to the point, the type of method that I'm using, to my knowledge, is the first being used on this species. So I can't make any comparisons to past historical work. So all of the knowledge, the data that is coming out of this project is coming from the work that I am doing. And so far what I would have expected for Denali is I would have expected a lot of ground squirrels. Denali, which is in the interior of Alaska, is right in the Alaskan range. So there's plenty of mountainous areas which ground squirrels are heavily associated with. And what I found, at least using this method so far, and we have to collect multiple summers of data in order to, be for sure in our estimation of how many ground squirrels there are. But I'm not seeing a lot of ground squirrels for what I would have expected.
Oh.
Do you think maybe there's just one really good grizzly bear just getting all of them?
I've seen a really good grizzly bear go through a lot of effort to get one, so it's possible.
You watched that happen? You watched a grizzly bear?
I watched it
chase down a
happen,
squirrel?
and I was rooting for the squirrel, but the squirrel didn't get away. So actually, it was a sow, which is, it's a female grizzly bear with her 2 cubs, and the ground squirrels, they're a couple of feet below the ground in their burrow, and grizzly bears, they're just powerful animals, and you could see her just uprooting and digging up all of this soil, and you see the ground. You could hear the ground squirrel, making its alarm call from the burrow, and so the mother.
Was it a really intense alarm call? You're alarm call squared, grizzly bear incoming, pounding in her. Okay, sorry.
It's the type of response you expect if somebody jumped on your back without you expecting it. It's just a scream.
Yeah.
That's how I interpret it, at least. And I'm this ground squirrel is screaming for its life, which. It's kind of sad, but that's how nature works. And you could see just all of this effort she's putting in. She just has really huge shoulders, so she's just really putting in work to removing all of this dirt. And the ground squirrel manages to get out of the hole and run away from the mother, but one of the cubs actually catches it as it's running away from the mother.
Oh, family teamwork.
Family teamwork.
Did you Snapchat that?
I do have a video of it.
You'd be Instagram famous if you just went out there. Just got today on Nigel's Instagram, bear versus squirrel part 2. The reckoning.
The reckoning.
I didn't see that coming, that the bear cub would be on the side.
Yeah,
ready to catch.
You can kind of tell they were kind of also annoying the mom as well, because their head is right where she's trying to dig.
Oh, really?
And eventually they just kind of get bored, and so they sit on the sidelines, not even actually paying attention to what she's doing. And so the squirrel could have made it, but it just ran right into the view of one of the cubs.
And they're basically just Mom, what's for dinner?
Yeah, exactly.
She's ground squirrel. We're working
squirrel.
on it.
They call them squirrel burritos.
So was that the closest you've been to a grizzly bear, when you saw it hunt down that squirrel?
No, unfortunately. The closest I've been to a grizzly bear is probably, I would say, between 20 and 40 feet. And we were both on the opposite side of these bushes. So we both didn't know that we were there. And it was another instance where it was a sow with two cubs, which is not the ideal situation because they're pretty protective of their cubs. And so what ended up happening is that there was a bus and they're like just waving at us out the window, me and the field tech that accompanied me throughout the summer. And it's like, bear, bear, bear. And I don't even like try to look around. I just run and get on the bus. And as soon as we get on the bus, we're like looking over the window, over the row of bushes, and there's the sow with her two cubs.
Oh, wow. Okay.
But I'm alive to tell that story.
Yeah. So did you, you said you also did field work in Siberia?
Yes.
What was that like? How long were you out there?
So I was out there with the program, the Polaris Project, which is a research experience for undergraduates. This is an REU. Maintained out of Woodso by the Woodso Research Center. And so what they do is they take undergraduate students to the Arctic and they expose them to doing Arctic research. And so while I was there, part of the work that's folding over into my dissertation work is one of the main concerns with the Arctic is their influence on our global climate system. And so when you think about climate change, really we're just talking about our atmosphere, which we typically think of as air, but which is really, just a composition of gases. And what's really unique about the Arctic is that the type of gases that are in the atmosphere is also locked in the soil, so carbon dioxide. And the type of gases that are locked in Arctic soil is about 50% more than what's in the atmosphere. And when I say locked, it's under ice, it's frozen. And so one of the concerns with climate change in the Arctic is that, this permafrost is melting. And so the concern is that a lot of the carbon that are in these grounds will then be able to intermix with the atmosphere, making our climate change dilemma that much more of a scarier prospect. And so while I was there, one way to look at this is what are the physical determinants of how carbon dioxide is going to leave out of the soil. And so ground squirrels, they live in the ground, and in this process, they're mixing the bottom layer with the top layer, they're fertilizing the soil. So what they're really doing is creating these ideal conditions for bacteria to go in and interact with, these carbons and release them to the atmosphere. And so,
wait, so the squirrels are making it worse? Is that basically?
We need to release some grizzlies out there.
So, by all means, humans are the number one contributors to gases that are being released into the atmosphere. And so what I'm doing for Arctic ground squirrels is looking at how are they influencing the physical properties of the soil, and what does that mean for the release of carbon dioxide. And so I unfortunately don't have a definitive answer for you. But one other way to look at this are beavers. Beavers in terms of like species are equivalent in terms of like how they can impact the natural environment. Like there's like a lot of flooding. They, create and build these like huge dams. And so, they're kind of doing the opposite in terms of what Arctic ground squirrels are doing. So instead of directly impacting the soil through improving conditions for carbon dioxide to flow out, beavers, what they're doing is instead flooding these environments. And so what you have is, instead of carbon dioxide being released, you have methane being released. And methane, correct me if I'm wrong, is about 4 times a stronger greenhouse gas than carbon dioxide. And so, that's also one way to look at how animals are influencing how carbon dioxide is going to be released into the atmosphere as well.
I remember not too long ago, there was some Republican politician came out and was like, this is ridiculous. We got to stop worrying about humans' effect. It's cows farting in the fields, all the methane that they're producing. We got to get rid of all these cows.
So cows are certainly, our agricultural practices is certainly one of a major contributor to greenhouse gases that we're putting into the atmosphere. And so he's correct in identifying it as a source of, these greenhouse gases. But will entirely removing cows, is that the solution? Probably not. But he's definitely correct in identifying it as a source of major greenhouse gases.
So we really have like several new villains in the climate change issue, though. It's like not just humans, although cows are domesticated, so it's kind of our fault too.
The amount of cows that are out in the landscape is certainly by our own hands in terms of, our agricultural practices.
Yeah. Those squirrels, though.
Yeah. The squirrels, though.
The squirrels are the new villain.
They're the new
I think we
villain.
can pretty much pin it on them. Like, if something bad happens.
Get rid of them. Get rid of beavers. Buy a Tesla. You're good.
So yeah, you said you went to Siberia as part of an REU program. That's a National Science Foundation program.
Correct.
Got a lot of acronyms here. NSF REU program.
Correct.
That's the research experience for undergrads. I also did that. It's a really great program that helps expose undergrads to what it's really like to do research. Kind of maybe like going in that vein, can you talk about how you ended up in the field that you did?
Yeah, so as a undergrad, my research was focused on infectious diseases, and I knew going into grad school that I did want a climate change component into whatever thesis or dissertation work that I did, because certainly climate change is also influencing how different animals and people are exposed to diseases, the conditions that either help diseases propagate more or reduce them more, and in the act of expanding my boundaries, I went on the initial trip to northeast Siberia, and the 9-hour flight from New York to Moscow, and then the 6-hour flight from Moscow to Yakutsk, and then the 2 to 3 hour flight from Yakutsk to Cherski. And in that process, I was just enamored by like these huge barren landscapes. No people were there. And, there's a lot of water in northeast Siberia, but it's just really beautiful and like really impacted me in a way that I didn't quite expect. I had never had that experience before. And also part of that experience was for the REU is that as a student, you are at the helm of your research. So you're designing the research project, you're coming up with the questions, and kind of being the lead on my own project, coming up with questions, and then getting feedback from the PIs who are on the trip were really formative in terms of my experiences as being a scientist. And all of that happened while I was in the Arctic. And so I just fell in love with it, and I took it with me to graduate school.
Nice.
I can't imagine taking a 17-hour plane ride and being like, this is my life. I love Coach.
So you started out in infectious diseases, did you say?
I started out in infectious diseases.
Okay. Did you always know you wanted to study science?
I always knew as a kid that I wanted to at least study animals. As a kid, I actually didn't get out to our national parks or even our state parks a lot. Most of what I seen came in through TV, so National Geographic, Animal Planet, Jeff Corrin Experience. So all of my formative experiences with science came through television, and then when I got to college, I got to immerse myself in those experiences that would eventually lead up to where I am now. But I always imagined putting myself in those wild spaces, those wild places, and I've gotten here, and it feels really great.
Is there anything else you'd like to say before we maybe move on and talk to Ruthie?
I mean, I'm also lucky enough that I can include my activism as a graduate student here on campus as well. So I've been involved with the Make It Safe campaign that's here on campus. I'm working with 3 other students now at the moment for our own lecture series. We're calling it Bridge. Bridge stands for Broadening Relationships, Impacts, Discussions in Geosciences, and Environmental Conservation. And we've gotten the support from the dean of our college, College of Natural Science. We've gotten the support of the chairs of each of our departments. So that's both the geoscience and environmental conservation. And part of our goals is to provide opportunities for early career scientists from underrepresented backgrounds to share their research and another broader aspect of their work as a scientist. And so we're rolling out this lecture series this semester, and I'm hoping for really great things. So that's also part of my time as a graduate student.
Okay, so up next we're going to be talking to Ruthie Halberstadt, who is a doctoral candidate in the geoscience department at UMass Amherst. How's it going, Ruthie?
All right. Good
So
to be here.
thanks for joining us. So do you want to just talk first about the research you do? Just tell us what you do.
So I study ice sheets in the past and in the future, and I use numerical modeling to reproduce their behavior. But I also go and do like glacial geology, and so then I tie together those geologic data with the models to try to make the models most accurate and robust. Because if you're going to build some buildings on a coast based on future sea level projections, you're going to need to have the best kind of ice sheet model. So everything is really interconnected in terms of, what happened in the Miocene 15 million years ago and what kind of building you want to build in Boston over the next 30 years. I mean, it's all very tied together, which is an exciting place to be in science today. So I've gotten to go to Antarctica, which has been a really awesome experience twice. And one time I was on a boat for 2 months, and I was mapping the seafloor, and from those features I can reproduce what happened to the ice sheet throughout the last glacial maximum. So I was looking at a time period about 12 to 8,000 years ago, and so I can basically map what happened to that ice margin throughout that time. And the second time I got to go to Antarctica, I was camping, which was quite an experience. And I know you're all dying to know how I went to the bathroom in the field, because that is everyone's first question. And because the Antarctic is such a wild place, it's very well protected. There's an Antarctic treaty that dictates how all human activity has to go in Antarctica. And it's very strict on this leave no trace. So yes, all of our poop buckets are helicoptered in and out. And you're not allowed to pee on the continent. If you go on a hike, you have to take a Nalgene water bottle, and then you pee in that, and then you empty it into the buckets, and then that gets helicoptered away as well. So yeah, I wanted to make sure
that's
I
like
included
leave
that.
no trace extra.
Yeah,
but
it's
like
crazy.
if they were like, okay, so anytime you need to poop, we're gonna just scramble some Apaches for you. I'd be like VIP status.
Well, what we did in the field is we constructed, so there were these little hills, and so we decided that the toilet area was going to be behind some of these little hills, and then we made little ice blocks around it. So there was kind of a little area, and then there was a flag you put up. So if you were using the bathroom, you put the flag up so no one would walk over the hillock and see you using the restroom. And they also had these little toilet seats that you take when you're assembling all your gear. You take little toilet seat, and then you just attach the toilet seat over the bucket, and so it is quite luxurious.
Wow, I feel like if you trained to be a helicopter pilot and then your job is just to shuttle human excrement off of Antarctica, that would be kind of a drag maybe. I don't know.
But also, how
I guess
fun
it's
would
all
it be?
frozen, so it's not
How fun would it be to drop a hook in the old crane game, just try to move the helicopter to get the bucket.
Well, we also had an episode where a helicopter dropped all of our gear, which was really unfortunate because it's so windy. This is kind of cool. It's so windy in Antarctica because there are these gravity-driven winds that come over the ice sheet, but there's no friction to stop them, right? There aren't any trees. So it's just this wind that's moving over a really, really smooth surface. So it ends up going really fast. So it's super windy. So anyway, so this helicopter was coming with our gear to drop it at the site, and then we were going to come over in the next helicopter. And it's got all our gear in this sling underneath the helicopter. And apparently it got really windy, and I didn't know there was a big red button that you could press on a helicopter, but the pilot pressed the big red button, and the entire sling was disconnected. And because he was this thing is moving around unsafely. Anyway, so all of our stuff broke. And so then we had to go back and re-equip. Oh, and the worst part is that we had a bunch of beer that we were bringing. And for some reason, the only thing that survived, the tents were broken, the food supplies were broken, but this beer was not broken. And they happened to land near a camp, like another temporary field site. And so they radioed in and they were like, oh yeah, we like looked through the stuff. It's all broken except for the beer. And we were like, great, we'll pick it up. And we never saw that beer again. Because it's a hot commodity.
I would imagine it's in short supply.
Yeah. Anyway. Right, so I study sea level rise. And the time that we were camping in the field, we were actually collecting a permafrost core in this area where there's not a lot of ice cover. It's called the dry valleys because it's originally named dry valleys because there's not ice there, but the dirt has been frozen for about 14 million years. And we were studying the time period right before it was permanently frozen in the mid-Miocene, which is the last time that CO2 levels are above about 400 ppm. And for reference, the current CO2 levels are above 400 ppm. And so the last time this region was not like permanently frozen was a time that's like 14 million years ago, and similar to what we're headed into. So, I mean, we really have no idea. I mean, we talk a lot about climate change, and talking heads and politicians talk about things they don't know about, and scientists talk in ways that nobody understands. But I mean, the bottom line is we are headed into a time period where we have no idea what's going to happen. It's completely unprecedented, and it's kind of scary. Like I'm thinking about this time period, 14 million years ago, the last time we've seen similar conditions as today, and we just don't know what's going to happen. But it's a great field to be a scientist in because there's a lot of questions.
So how do we know what happened 14 million years ago?
Well, we don't know what happened globally. We know what happened at teeny little pinpoints, such as this core that we're taking. We can reconstruct temperature. Actually, some of the ways that we can do that is we can identify fossils of bugs, and then we can say, okay, this fossil of bug is really similar to this bug that lives today at a certain temperature range. Or leaf, so there were actually vascular plants living in the mid-Miocene at this time where it was about, we think CO2 is about 400 ppm. And so we can say, okay, this plant looks like this leaf fossil. So I was actually digging up fossil. Oh my gosh, and I found this like little knob, this little stick in this like fossil lake. And it wasn't, when I say fossil, I mean it was an imprint because it wasn't fossilized, it's just been frozen. So it was like actual wood. It hasn't been replaced by minerals. It's like actual wood that's 14 million years ago. That was like crazy. But yeah, so we use bugs and leaves and use modern analogs for ecology to know temperatures. But that's a postage stamp. And then the challenge is finding other little postage stamps across the globe to try to recreate conditions.
So you said that this is the first time in 14 million years since we've had this, and we have no clue what's going to happen. So isn't there a chance it's just going to be great?
I mean, it'll be great for some people.
What if this makes America great again? What if the 440 ppm is what it took?
So climate change is okay, first of all, we do have some idea. We just don't have a very good idea in what people would like to see. We want, like a politician or a citizen will want a scientist to say, like, this is exactly what's going to happen in 10 years, right? Like, we can't do that. But we do have some sort of ideas from these little postage stamps. So that was a bit of an exaggeration. The other thing is, so climate change is like this big complex thing, and the thing that I know most about is sea level, and the thing that Nigel probably knows about is ecology and air temperatures, and those are two completely different study areas. So we're recording from Massachusetts now, and I've done a project in Boston about predicting sea level rise in Boston over the next 100 years under different greenhouse gas scenarios, right? So what will happen if the current levels of emissions stay exactly the same, which is not going to happen. What will happen if we continue doing business as usual, and then there's some like in-betweens, like what will happen if we like kind of commit to this but then like ghost on it later. And so then you can actually translate those greenhouse gas scenarios using these models that I work on of ice sheet contributions, and then you distribute that sea level contribution from the ice mass loss along global coastlines, and you say, okay, what's going to happen in Boston? And so you can actually predict where those flooding areas are going to happen. And one thing I've worked on is looking at the areas that will be inundated, not only like, and I say inundated, I mean like actually underwater. There'll be areas that will be actually underwater, but most significantly in the next 100 years, there's going to be a floodplain expansion. right? So when you have regular floods, what's going to get flooded when there are these storms? And so I've been looking at how that interacts with demographics, like people who don't have cars, like especially in Boston, people who are elderly and may not be able to be evacuated, people who are already under financial strain, people who are minorities or don't speak English and can't read like evacuation warnings. So there's this really huge, complex problem we have ahead of us.
So you spend a lot of time comparing the historical amount of greenhouse gases with what we currently have in the atmosphere. Taking off your academic hat for a second, do you think about, or do you have an idea of what we can do now in terms of like reducing what we're putting in the atmosphere?
The biggest thing that we can do is not pretend that climate change is a political issue, because it's been turned into this thing that people win and lose elections based on, which has nothing to do with climate change, right? I mean, I think we need to turn it back into a science issue, and once it's a science issue, then we separate that from the political side and let the politicians deal with it. But now, if you're in a different party, all of a sudden you have an opinion on climate change, like that's slowing down all of the mitigation efforts, and that is like, it's just, we've come to a complete halt on trying to mitigate our emissions because of this political game. And I think probably the most useful thing we can all do is bring climate change back to science, and then let the politicians deal with the mitigation part, rather than letting the politicians into the science and then letting the scientists into the mitigation.
What would you say to somebody who is a climate changer? Like my mom, I had a conversation with her around a year ago, and we were talking about climate change, and she was like, well, there's a lot of scientists who don't agree with climate change. There's a lot. And what the mainstream media is saying is that it's 99%, but it's not 99%. And there's a lot of science out there that's saying that it's not true that climate change is happening. So what would you say in like a layman's term to those people that feel that way?
Well, so that particular assertion, I think, has everything to do with how climate change is portrayed in the media. Whereas if we were on another kind of radio station, and maybe I was somebody who was, putting on my science communication hat and saying, like, let me tell you about climate change, and then, Laura as the host would be like, okay, well, if we have someone who's going to talk to us about climate change, we have to have someone who's going to talk to us about how climate change isn't real. And so then you're setting up a 50-50 boundary between like a scientist who studies climate change and someone who's just going to start doing, data cherry picking and all of those things that give you attention. And so that portrayal makes people who don't study climate change feel that there's not a 99% scientific consensus about climate change. So that is like a totally political tool to grossly overrepresent this small contingent of people who are generally associated with oil and gas, although, staying away from that agenda here. Nigel?
So I really think it's important for us to also meet people where they are. And so instead of working from, this knowledge deficit point where, they just don't know enough, or they just don't have all the facts right. Well, like, how about instead, how about we start having conversations about what they don't know, what they do want to know? Because I'm sure your mom is curious at least about some aspect of climate change. And so you don't have to debate, what the media is portraying. You don't have to debate the amount of scientists that have consensus on, how much of climate change is contributable to humans. But I would think what you can have is a conversation on, okay, so, what are your questions about climate change? What aspects of it are you curious about? And you can go from there.
Yeah, what I would say to your mom is, I'm sorry, it's really hard to find the credibility of information. There is so much information online and in all this media, on TV and on, books and everywhere, and there's just like so much information. And even if I'm surfing online, I like search a question related to climate change, like I have to like read up on the opinion pieces on any source before I trust it, because there's so much twisting of information. So I would say, like, I'm really sorry. It's so hard to get reliable data or any kind of information. So I would say, like, you should talk to a climate scientist. But of course, like, not everybody has access to climate scientists. And mostly, like, what I want to do when I go home for Thanksgiving is, like, eat the food, And, I like talking about this to an extent, but it's really hard, and I don't really have an answer there.
Well, luckily we have 2 climate scientists with us today, so we're helping to rebalance that spreadsheet. But I really like the point you made about meeting people where they're at and like asking them questions instead of coming at them with information that they may not want. That's a really good point about how to have a more productive conversation with people who may not be like on your side from the get-go, but being willing to hear them and then them being able to hear you when you're talking about the things that they want to hear.
So there's another issue in climate change communication where people are like, oh, there's been like all of this snow, so global warming isn't happening. And there's just this really unappreciated aspect. I mean, we've now switched terminology to say climate change because it's a complete transition of a system. It's not like a linear trend towards warming, although on average that's what it is. But this variability is so underappreciated, and so the same goes with sea level. If we say like, okay, we're taking a certain amount of gigatons of ice off Antarctica, like all of that's melting going into the ocean. So you have this transition of mass from an ice sheet into the ocean, and then I think most people would be like, oh, okay, like sea level is going to rise everywhere by like that amount divided over the area of the ocean. But that is like absolutely not what happens. In some places, sea level actually falls because sea level, so sea level is not a bathtub is like my bottom line here. What happens in like the areas around Antarctica, for example, if you take mass off of that continent and you put it in the oceans, all of a sudden you're not loading the ground underneath Antarctica as much. And so that the ground actually rises on timescales that are relevant. And so you have a relative sea level fall around Antarctica. So what I'm saying is if you melt ice from Antarctica, sea level falls around Antarctica, which is completely non-intuitive. And so and that effect can that effect influences the entire southern hemisphere. Similarly with Greenland loses mass, the entire northern hemisphere is affected by this like ground movement. So that's one non-intuitive part of sea level. And the other one is the gravitational effect, which I think this is like my favorite thing to talk about because it's not like scientifically polarized, and I just think it's really interesting. So you know how gravity works, where you have a big mass, a little mass is attracted to a big mass, and we think about on Earth as gravity being like, if you like jump, you're going to be pulled back to the center of the Earth because the Earth has this huge mass. But the same thing actually works laterally. So if you have like a big mountain that you're standing next to, you're like kind of a little bit attracted to that mountain, like sideways, because that mountain has mass. And so these ice sheets on like opposite sides of the Earth have a lot of mass. And so if you take away some of that mass, you're actually losing the gravitational attraction of that ice sheet to sea level. So right now, sea level is way higher, I would say objectively, but anyway, let's just go with that. Sea level is way higher objectively by ice sheets than it is away from ice sheets, because the ice sheets are actually pulling the ocean water towards them gravitationally. So you also lose sea level when you melt ice off of Antarctica, for example. Not only are you rising the land and causing a relative sea level drop, you're also losing that gravitational attraction of sea level to the continent. So there are all of these complex ways that sea level is like not a bathtub. And so when we're trying to predict sea level, we have to not only use these ice sheet models to predict how much like warming air temperature and ocean temperatures are going to melt the ice, but then we have to figure out where that mass is going to go. And so it becomes this really complicated problem and really critical one, right? So people on global coastlines want like a 30-year prediction of sea level rise. And so the scientists are back there like furiously trying to figure out like how the system is evolving. But it's a really interesting problem too.
That's really interesting when you talk about the way that the ground reacts, the ice being taken away. That's something that we're even experiencing in New England still from the last glacial period, right? Like 10,000 years ago, the glacier melted, and that's why like the coastline of Maine is really rocky, is because it's still bouncing back from that.
You can just look on a map of like land movement, and you can see that response. So land movement is still moving up where it was covered by ice during the last glacial maximum.
So Ruthie, do you want to talk about how you ended up in this field of research?
Sure. So I was an undergrad, and I didn't know what I still don't know what I want to do. But when I was in undergrad, I really didn't know what I wanted to do. And I was interested in earth science. Well, originally I was an engineer, and then I was like, I don't want to sit at a desk and like look, sign off on things all day. So I also added earth science, and I ended up doing research with this professor, doing sort of Antarctic research. And near my graduation time, I was like, I don't know what I want to do. And I was kind of chatting with him about it. And he said, oh, we have like a trip to Antarctica planned. Do you want to come? And I was like, heck yeah, sign me up. And so then he was, oh yeah, that's great. Well, if you're going to do this research for this trip, like, why don't you do your master's? And I said, all right, sounds good. So I did that. And then I was like, wow, I love Antarctica. This is addicting. Like, I want to go back. And then my current advisor came and gave a talk at Rice in Houston, and that sounds really interesting. And then I was just chatting with him, and I was, maybe I could do my PhD. So like, you're looking for students? And then I didn't apply anywhere else, and I ended up here. I mean, it's been, yeah.
So it was, sorry. Yeah.
I was just gonna ask, when you went to Antarctica, what about Antarctica was it? Was it the plane ride? Because I hear scientists love plane rides.
It's actually kind of cool for all my like plane nerds out there, because we got to ride in like a military plane. It was a C-130 with troop seating, and so you feel pretty special, right? You can look out the little windows.
Fun fact, that's only fun the first time.
Yeah, I found that out the second
fifth time you're on a military plane, you're
Yeah.
like, this isn't fun. There's no air conditioning.
Like, where are my earplugs?
Spotify doesn't work on this thing.
Yeah.
So it sounds like your planes got more sophisticated while my planes became less sophisticated. So happy for you.
Okay, I think we're ready to move on to the last part of our show, which is going to be a little game that I've come up with called GTA. Not Grand Theft Auto.
Okay.
No, I mean, that's a great game, but that's not, I didn't invent that, actually. No, it's guess the acronym, because in the sciences, we love to use acronyms, and there's a reason. It's because we talk about certain topics a lot, and we have kind of a common language with the people who are experts in those topics, and it makes it easier and faster to talk about them, but it can kind of leave science feeling inaccessible. So I've compiled a list of some kind of climate change related acronyms, and so what we're going to do is we're going to have Taylor, who is our non-scientist co-host, guess what these acronyms are, and then we're going to see if Ruthie or Nigel can step in and help him when we get there.
I think I've got an advantage here because I am in the Army.
Mm-hmm. Yeah, you
So
might actually know a lot of these.
Yeah.
I don't know. I'm really curious. Actually, I mean, I'm curious in general, like what acronyms the general audience might know or not know, but I kind of have a spread here. So we'll start with IPCC.
Oh, that's my favorite kind of beer. That's Indian Pale, cut from the corner of, what was the last letter?
It's IPCC.
Got it.
There's two C's.
Cut from the corner.
Does anybody want to jump in? You guys know what it is?
It's the
Intergovernmental Panel on Climate Change.
Yeah, so that's a worldwide organization kind of scientists who get together. How many years do you guys know? Every 3 years.
Four?
They make a big report about the state of climate change science.
The sea level section, which means that I do not ever see him, but it's also very exciting.
Very exciting, because it's really, that's the universal source of
that is
this is what's
source.
happening with climate science.
Globally.
It also shows the collaborative spirit of scientists, not just from the United States, but from across different nations. How we're like pulling all these resources together.
Yeah,
to,
although we
understand this.
might not be funding the U.S. might pull their support of the IPCC for the next cycle, which means that it would not be able to continue. So we would have no gold standard source on climate change information.
Oh wow.
anymore.
Okay, our next acronym, GCM.
GCM. Golden Chassis of Merwin. Merwin, of course, is a wizard, and that's his golden chassis.
And that relates to climate change
because it's a story about how his golden chassis he distributes greenhouse gases. That's how you get. It's a children's book that describes how climate change
Climate
works.
system is certainly magical.
Yeah, exactly.
Does anybody else want to jump in? Do you guys know what GCMs are?
Global climate model.
Yep.
I was close.
Nice.
Good question to female. Do they also call them circulation models as well?
For GCM. Oh, global circulation? I don't know. I've only heard global climate models.
I saw online general circulation model also. So that's kind of
There's like a
two
derivative.
relevant climate change types of models. But yeah, this game was a little bit inspired by a talk that was given by somebody a couple of years ago from the Northeast Climate Science Center, actually, in our department. And the title of the talk was GCMs of Ms. 19 and 23. MIS, and he started his talk and he's like, well, it's pretty obvious from the title what I did. And he was completely sincere.
Wait, are we gonna have Taylor guess the MIS is?
Yeah, okay, I guess we'll move on to our next acronym, which is MIS.
MIS. The Mission Impossible series.
Actually, I think that's accurate, but not the one that I was going for. Anybody want to step in?
I actually don't know this one.
Ooh.
Marine isotope stage.
Marine isotope stage. So this is one's a little bit deeper into paleoclimate stuff. So this is basically, so they study the isotopes from the water of the ocean going back in time, right? And I guess I should say what an isotope is.
Maybe we should just skip this.
This is a lot of
That's
info.
an important distinction that we probably didn't speak about earlier, but Ruthie is focusing on more of a paleoclimatological focus. Paleoclimatological. You know what I'm trying to say.
The history of
the
climate.
history of climate, and I'm much more focused, here on the current.
Yeah. And so one way that we understand the history of the climate is using isotopes, which is basically, do you know what an isotope is, Taylor? I'm curious.
I am familiar with the term isotope, but mostly in regards to nuclear issues.
Yep.
So I assume it's like part of a molecule?
Yeah, so it has to do with like an element. So basically, like, let's take a common element, oxygen. And so I forget what the typical weight of oxygen is, 16? Yeah. So every element on the periodic table basically has a weight that it's like standard weight. So it's made up of protons and neutrons, and that's what defines it as that element. So oxygen usually weighs 16. So we say that it has an atomic mass of 16. But once in a while, you'll have an oxygen that has one extra neutron. So the number of protons determines that it's oxygen, but you get an extra neutron and suddenly it weighs a little bit more. Or sometimes you'll lose a neutron and it'll weigh a little bit less. And so those variations in the weight of oxygen are called isotopes.
Gotcha.
And so that's important because like when you have a hotter climate, lighter oxygen is going to come out of the water preferentially because it's just a tiny bit lighter, so it'll behave a little bit differently. So you can learn a lot about the climate from like just studying isotopes buried under the ocean so anyway, this is a really deep one. Maybe I should
but I think that's a really important point to make because I'm talking about like 14 million years ago. Like, how do we know what the ice sheets and sea level was 14 million years ago? Or like, how do we know that sea level is like rising compared to previous times in our history? And I think that this is the foundation of paleoclimate, basically, is this oxygen isotope record. Because what happens is, so when you have lighter oxygen molecules, and the hydrologic cycle happens when you like evaporate water from the oceans, and then it gets carried and it rains on land, and then the like river systems route that back into an ocean. It's a cycle, right? But if you have ice sheets growing and you rain on an ice sheet, that water is just going to stay on the ice sheet. And so what happens is you preferentially evaporate lighter oxygen molecules, and then you bring them over and you rain them on the ice sheet and they just stay there. And then you evaporate more light oxygens and you move them to ice sheets. So eventually the ice sheets are full of really, really what we call isotopically light oxygen molecules, and the oceans are full of really, really isotopically heavy molecules. So if you are measuring like little organisms at the bottom of the ocean that are recording the isotopic concentration of the water in their shells, and you measure like there's a whole bunch of heavy oxygen isotopes during this time period, then you infer from that there's a lot of ice sheets that are like basically like securing all of this light oxygen isotopes on land. And so what we do is we can like take really deep ocean cores and we see this like all these wiggles of oxygen isotope ratios, and we say, okay, we are interpreting this as like sea level. Like this is a proxy for sea level, and this is a proxy for ice sheet growth and retreat.
So coming back to our acronym, just to make sure we focus on the acronyms here. No, so marine isotope stages is this kind of like consensus of scientists saying going back in time periods and saying like the isotopes were mostly this way at this time, and they have just like a number system. So like marine isotope stage 19 is like a set time interval in history basically that climate scientists use to talk about how things have changed.
I don't know what happened then though.
You don't know the
I
time
don't know
period of
specifically.
MIS 19? No, I don't think
That's the
most
one where
people do.
Tom Cruise is so old. He's just climbing with his oxygen tank.
Okay. GHG.
GHG. Global heat guesstimations. Which is what these liberals have been making for decades.
That was a really good guess.
Thank you.
But not quite there. Ruthie, you want to jump in?
Greenhouse gases.
Greenhouse.
Oh, shoot.
Okay, I have just one more. Okay, our last one is actually a really tough one. ENSO.
ENSO. All right. Environmental Neuroscience Systems of Operation.
I would like to know what that would involve. Environmental neurosystems. I almost like am imagining like the brain of the planet,
Yeah,
like
yeah,
changing everything.
Exactly.
Yeah.
The
Not-
brain of the planet being the isotopes in Antarctica. Yeah.
I like that.
Okay.
Antarctica's the brain of the planet.
Yeah,
I like
it's
that.
definitely like
I can get
hat.
behind that.
And then you go into that hat and you see the brain.
Totes.
Okay, well, it's wrong. I'm
Uh-oh.
sorry. You are not right. That's not what it is. Does anybody know?
El Nino seasonal oscillation?
Seasonal
Southern
oscillation.
oscillation? Seasonal
Oh,
oscillation?
southern,
Southern
Southern
oscillation.
oscillation?
Yeah, El Nino southern oscillation. Can you explain that?
Oh, gosh.
I can't. No, a little bit I could, but anybody know?
If this was Who Wants to Be a Millionaire, I don't think we'd be walking out with any
Ooh.
cash right now.
We don't have any ocean scientists here, actually.
Yeah, but I was
right?
about to say, like, you guys have the best lifelines. Like, if it was a science question, you were like, I'm going to call, I don't know, my advisor or any of my scientist friends.
Yeah.
So
true.
El Nino southern oscillation is like the way that the ocean temperatures change predictably, kind of. And I feel like most people have heard of El Nino.
Sort of predictably.
And like sort of cyclically, how
Yeah,
about that?
yeah.
Not necessarily predictably, but
Yeah.
cyclically. We have El Nino and La Nina.
That's why sometimes it's anomalously hot. And there's like a lot of precipitation. And then the talking heads are like, oh, it's an El Nino season, as if that explains all of our climate patterns.
Which is like when the Pacific Ocean is warmer, right? And the warm air comes in.
I don't remember which one is which. Because there's an opposite where there's El Nino and there's La Nina. And I don't remember which is which.
But you bring up a really important point where, like, we have this network of scientists that we can call and rely
Yeah.
on. Like, I work on climate change issues, but I am not an actual person who studies climate. But we do have other scientists that we regularly engage with that do have these answers. So an important part of our work is making sure we do reach out and we're forming these deep connections with our other scientists because they are ultimately informing our work.
That's a really good point. That's the entire process of science, really.
That's the entire process.
Is talking to people. No, okay, not just that.
Like,
But
what have I
I'm
been
like,
doing
this
this
is
entire time?
Well, that's
This
a
is
great way to
basically
end a radio
science.
show.
I'm like, talking is really the most important thing.
This has been science.
This has been the pinnacle of science. Okay, well that's our show for today. Thank you so much for joining us. Thank you, Ruthie and Nigel and Taylor. Cool. Okay. Well, thank you guys.
Thanks, Laura.
You just listened to Lab Talk with Laura, hosted by yours truly, Laura Fataruso, with guests Nigel Golden and Ruthie Halberstadt from the Northeast Climate Science Center and co-host Taylor Ortiz. The jingle at the beginning of our show was written and produced by Matt Woodland. Keep it locked to 91.1 FM WMUA Amherst and stay tuned for WMUA news coming right up.